All right, so we're going to pick it up where we left off last time with the rules of differentiation. And so if you recall, there were quite a few of them. And so so far you can see there are 7 listed there. So we've managed to get through the first couple of them. Actually, we did the first 3. We did the constant rule, we did the power rule, and then we did the rule for sums and differences. All right, so those are very straightforward. Now we're going to tackle some of the more complex ones today. And you'll see that in some cases, they're really just extensions of the previous rules. So just as a quick reminder, the derivative of a constant is equal to 0. Okay, now when you think about it, it makes perfect sense because remember, a derivative is itself nothing but a rate of change. So of course, the constant never changes. Therefore, the derivative of a constant has to be 0. Now, we also did the power rule. Now, this is going to prove to be one of the more important rules. Anytime you approach a polynomial with this power rule, you're going to follow the same steps, assuming that you're looking at a function that takes the form kx to the n power. K is the coefficient or constant in front of the x, n is its exponent. And the derivative of this expression is equal to n times k times x to the n minus 1 power. Just as a quick example, if we start with f of x equals 3x to the 4th, then that means that k is 3 and n is 4. And so remember, the derivative here is going to be n k x to the n minus 1, which means that it will be 4 times 3 times x to the 4 minus 1, which is the same thing as 12x to the 3rd power. Very good. Now, here's another example we did last time. So really, it really all just comes down to remembering this key formula right here. This is our power rule. How about this one? Now, it can get a little messier when we have negative exponents, but the principles are the same. We have a k here, and we have n here. And so since k is 6, n is 3, the derivative, when f of x, again, is kx to the n, must be n k x to the n minus 1, which in this case would be negative 3, 6, x to the minus 3 minus 1, and that in turn gives us minus 18, x to the minus 4th. So, by the way, I do want to point out something interesting here. We can prove the constant rule with the power rule. Let's just do that right now, just as a quick example of how this works. Suppose that I had this. F of x is 3. Now, if you think of this as equivalent to 3x to the 0 power, which it is because x to the 0 power equals 1. That being the case, that means that k is 3 and n is 0. So we apply the power rule. Look what happens. We have 0, 3, x to the 0 minus 1 power. Now, the presence of the 0 guarantees that no matter what else follows it, we end up with 0. So this is going to show you that there's a reason why, besides the logic of the fact that, like I said, the derivative is a rate of change. But I mean, in terms of the rules of calculus, this is why the derivative of a constant is equal to 0, because of that n. Okay, that n is always going to be 0, and therefore the derivative has to be 0. All right, and now if you recall, we also did the rules for both sums and differences. And you'll recall this is a very straightforward concept because we saw here, for example, that the derivative of a sum is equal to the sum of the derivatives of the individual functions. So here, for example, we saw that if f of x equals the sum of g of x plus h of x, then the derivative f prime of x is the sum of g prime of x and h prime of x. Okay, and the same thing holds if there are differences. So it's a very straightforward rule or set of rules. And so we did a couple of examples where we get a chance to practice with the power rule. For example, here with g of x, we have a polynomial where k is 3 and n is 2. And remembering our rule, for g, we'll have 2, 3, x to the 2 minus 1 power, 6x. For this one, h prime of x, k is 1 because there's an implied 1 in front of anytime you see x by itself, there's an implied 1 coefficient there. So k is 1 and n is 3. So therefore, h prime of x using the power rule must be 3, 1, x, 3 minus 1, 3x squared. So the sum is just the sum of those two derivatives. Okay. So, and then we bring them together and we end up with 6x plus 3x squared. Okay. And, you know, like I said, the same thing would hold true if there if this was a subtraction question. For example, we had something like this. Okay, so this is our g of x. This is our h of x and g prime of x. Because this is k and this is n, we're going to have 4, 3, x to the 4 minus 1, 12x cubed. Aha, now this one is a constant, where for this one, k is 1, n is 0. So therefore, based on our power rule, we're going to have 0, 1, x to the 0 minus 1, or just 0. So f prime of x will be g prime of x minus h prime of x, or very simply 12x cubed minus 0, or we can simply write that as 12x cubed. All right, now this is where it starts to get more intense, the product rule. You might think, based on what we just saw here, that if I had a function which consists of a product of two other functions, then the derivative of the product is just the product of the derivatives. But unfortunately, it's not quite that simple. Okay, so instead, here's what happens. And you can see, well, you know, it's a little bit messy, but we'll get used to it. Don't worry, we'll get plenty of practice with this. So if you have a product of two functions, then the derivative, and which, by the way, we can write this in different ways, but we're going to do it here as g of x times h prime of x plus h of x times g prime of x. Now, at some point, you'll have done this enough times, you'll have it memorized. If we're in a normal classroom setting, you'd probably want to sit down and memorize this. Because we're online, it's not quite as important, but I think at some point, if you're going on to Calc 2, these rules, you really should make an effort to memorize them because it'll come in very, very handy in your future math classes. But, you know, right now, we just want to focus on understanding what this is telling us. Okay. So here's an example. Now, by the way, this one can be solved in two different ways. I'll show you what I mean in a second. So here we have g of x times h of x, and we know how the power rule works. So for example, this first one, given that this is k and this is n, then we can go through the power rule And we can see that we have 6x. Okay. And then what about h of x? 2x cubed, this time 2 is, k is 2, n is 3. So again, using the power rule, we have 3 times 2 times x to the 2 minus 3 minus 1, or 6x squared. Okay, so what I'm going to do is copy all of this just to keep it all together in one place. Right up here, I'll put it up here so we can see it. G prime of x, we discovered is 6x. And then we discovered that h prime of x, using the power rule, is 6x squared. All right, now we just plug these in to this formula. G of x from up here is 3x squared, h prime of x is 6x squared, h of x is 2x cubed, and g prime of x is 6x. So when you multiply these out, of course, they will become simpler. And here, just by luck, I suppose, they both have the same exponent, so we can just combine these very simply into 30x to the fourth. Now, what else could we have done? Now, since this is such a simple case, it wasn't absolutely necessary to use the product rule. So what you could have done, and whenever you encounter a problem in calculus, you always can use, it's very rare that there's only one way of getting an answer. What you might want to think about doing is thinking about all the other ways you could solve for this, and then basically picking the one that is the easiest, because that will help reduce the risk of errors. So here, for example, look what we could have done. If you multiplied this out, you would have had 6x to the fifth, and now all of a sudden you don't need that product rule anymore. You just need the power rule. Okay, so this is good that we can use this as a double check. There's nothing wrong with double checking. It's very a very easy way to avoid mistakes. So we have 5 times 6 times x to the 5 minus 1, 30x to the fourth, and that's exactly what we discovered with the product rule. Very good. Now, when we're dealing with polynomials, it'll often be the case that something like this could be reduced to something simpler. But when we start looking at messier functions, like logarithmic functions, for example, or trig functions, then something like that is not really practical. You'll have to go ahead and use the product rule. But it's nice to know that for something like this, we can do it both ways and use that as a double check. All right, I'll tell you what, let's make up a new example here just to get some more practice. Let's say that f of x equals something like this. Okay, so once again, we can do this in two different ways. This is our g of x, this is our h of x. So using the power rule, g prime of x is going to be 2 times 4 times x to the 2 minus 1, which is 8x. Because, if you notice, and so the rule, of course, f prime of x is going to be nk x to the n minus 1. So that means we must have 8x. Okay. And then h prime of x will be 18x squared. Oh, actually, I should have written down the steps. Hold on. It would be 3 times 6 times x to the 2 minus 3 minus 1, which is 18x squared. Again, that's because h of x is 6x cubed, which means that this is our k, this is our n. And when you plug those into the definition of the power rule, you'll see that you will in fact get 18x squared. So now the derivative is this. And then we end up with 4x squared, 6x, 18x squared plus 6x cubed times 8x. And then we can combine these. We have 72x to the fourth plus 48x to the fourth, or 120x to the fourth. And just like before, we can actually do this a slightly different way by simply multiplying these out in the first place and then just directly applying the power rule. Let's try that. Again, it's up to you, whichever one works for you. So since it started out here, here's our K, here's our N. And again, remember the rule works like this, the power rule. So that means f prime of x must be 624 x to the 6 minus 1. Oh, I just realized I made a dumb mistake here. Yeah, this is 5. Okay. Yeah, that's why we double check, by the way. It's so easy to make mistakes like that. All right, let's try that again. So we're going to have 524 x 5 minus 1, and we're done. Very good. So we know that we did it correctly because they match each other. All right. Now, for the time being, since we only know how to apply these rules to polynomial, we'll carry on from here, but later on we'll revisit these rules when we start to introduce more complicated situations. And so we're going to now move on to the quotient rule. Now, the quotient rule is even messier, really, than the product rule. Again, it's not the case that all you're doing is taking the ratio of two derivatives. Here's what you have to do. Yeah, look at that. It's a bit messier, but we can do it. Not a problem. All right, so I'm going to show you a new example. I'll copy it back here so you can see it. Here's our rule. So here's the ratio. Now, by the way, again, if you could reduce this ratio by factoring or something like that, you could actually do that. But here, that's not really the case. There's nothing to do. There's no factoring available to us. So here, the only option we really have is to use the quotient rule. So first, remember that the numerator is g of x, the denominator is h of x. And so now we're going to take these two derivatives. We need the g prime of x, and we need the h prime of x. So we're going to actually apply the power rule to each term individually. Okay, and then combine them. So let's start with g of x. So for the first term, we have k and n. So based on the power rule, that gives us 6x. Fine. Now for the second term, you have to be careful with this one because minus x, there's an implied 1 coefficient, and there's also an implied 1 exponent. So this is our k, and this is our n. And so now we can apply the rule, our power rule, that is, and you'll see that we just end up with minus 1. Now the third term is a constant, so we know that that's just going to go to 0. But just in general, I just want to mention here, the derivative, if f of x is ax, the derivative is just very simply a. Okay. because according to the power rule, you see what's going to happen here. This is always going to be zero. So whenever you have the derivative of a constant times x, the result is just the constant. Okay. And so that's what happens here. Because the coefficient here is -1, the derivative has to be -1. And again, here, the third term, remember, we did show that the derivative of a constant is always zero. So what ends up happening here is that we have a very simple result. Here's our g of x. And based on our power rule, we end up with 6x minus 1. Okay, this term, the third term, has a derivative of 0. So there's only two terms now. H of x, same thing. We'll just apply the power rule for both terms. So for this first one, we have a k of 4, n is 3. And so we apply our power rule. All right, so quick reminder, k is 4 and n is 3 here. And so when you plug them in, you get 12x squared. Now for this one, we have to keep an eye out for that negative. K is -3 and n is 2. So when we apply our power rule, remember, k is -3. It's 2. And so by plugging those in, you can see we end up with -6x. So what we end up here is the derivative, h prime of x, is the derivative of these two individuals. This is the difference rule, by the way. All we're doing is taking the derivative. It's as if these were two separate functions and we're subtracting one from the other. So all we have to do is take each individual derivative and we combine them into our final result, which is h prime of x is 12x squared minus 6x. But we obtain these by applying the power rule to each individual term. So summarizing everything, here's the results. Now we're going to apply them into this rule. Okay, this really messy rule. Okay, so again, you can see the substitutions. Now, normally you, at the end here, you would try to simplify as much as possible. With such a messy expression, though, it may not be worth your while to do that because, you can go through an awful lot of algebra here and still end up with a terribly messy expression, which is the ratio of two different polynomials. So unless there's an obvious way of simplifying this, you may want to simply leave it the way it is. Okay. That's not to say that you shouldn't try to simplify it, but I would say that it's probably a little overkill. This is your answer. And unless it's really obvious that there's some common factor to all these terms, you'll probably want to just leave it like this. Okay, anyway, now what we're going to see now is an interesting idea. We're going to look at the so-called generalized power rule. Now, it appears at first glance to be very similar to the original power rule that we learned before. What's different is that you've got some general function of x here, which could be literally anything, and here's your exponent. Now, if you remember, here the derivative was n k x to the n minus 1. So here you've got this extra complication here. Because what's in the parentheses is a function rather than a constant, we need to not only take n g of x to the n minus 1 power, but we also need this g prime here. You can see this is getting complicated. The key to the whole thing is that there's a function in the brackets instead of a constant. Now, you could make the case that the power rule that we know is a special case of this one. Okay, because they're basically the same thing. It's just that this one applies to every case. The one we learn only applies to this specific case right here. So this is a very specific example of the power rule. This is the one that you can use in any circumstances. It's just that when you have something this simple, you might as well use a simple rule. Okay. But anyway, let's take it here. Yeah. See, now look, they're getting very complicated now. F of x now is 3x squared plus 4x minus 1 to the third power. So we're going to need g and g prime of x. And remember, in order to find g prime of x, we have to take the derivative of each of these terms individually. So if you start with 3x squared, then we're going to have 2 times 3 times x. That's going to be the derivative of this first term. And then for 4x, now remember, we did mention this is a special case. The derivative of 4x is just 4, okay? Because here, the exponent is 1. And so you have n, this is k, this is n. So nk to the x to the n minus 1 is 1 times 4 times x to the 1 minus 1, 4 times x to the 0, which is just 4, okay? And now, of course, this last one is a constant. It just drops out. The exponent here is 3. That's what this n means. So now, this is what we're going to do. Oh, there it is. It's already there. Okay, so let me just quickly remind you that let's copy these. All right, that's good. So we're going to plug in. Now remember the n. Oh, you know what we need? We need the original function. Whoops. There we go. All right, just so you can see, remember, so this is our g of x. This is our n. So here's g of x. N is 3. And g prime of x, we just got through solving for. So we get 3 times the original function squared now. Notice how we reduced the exponent by 1. And then out here we have g prime of x. So again, if you you can simplify this a little. This one you could rewrite it if you want. But unless there's a really good reason for it, you don't really have to simplify it any further. You could certainly apply FOIL to this term in brackets and then multiply it all out, but it's going to be very messy. This is probably good enough, unless you're looking for a specific constant result or something like that. Now, by the way, how do you know when it's time to use this? As long as your polynomial is raised to some power, the entire thing that is, then it's time for the generalized power rule. Okay. That really is how you know that it's time to use the generalized power rule. A polynomial, or actually any function of x for that matter, the entire thing is raised to some constant exponent. That means you can use the generalized power rule. Oh my God, look at this one. Oh, and by the way, we mentioned it once before that the derivatives we've been taking here are the first derivative. And the way it works, the terminology works is when you hear the word derivative, it's understood to mean the first derivative unless it says otherwise. So here what we're going to do is take this expression and not only take the first derivative, but the second and the third. And basically, all it means is that you start with your original function, you apply whatever rule is appropriate to get the first derivative, and then you reapply the rules to that first derivative to get to the second derivative. So in other words, the second derivative is nothing but, let's write this in here in English, the second derivative is the derivative of the first derivative. So you could think of it like something like this. The derivative of the first derivative is the second derivative. And that means that the third derivative is the first derivative of the second derivative rather. And you can keep doing this as long as you want. You can have an eighth derivative, a 10th derivative. It doesn't make any difference. You can do as many as you like. Usually in practice, though, we don't need to go beyond the second derivative, but it's always possible. So the third derivative is the derivative of the second derivative. Okay. So now you see here, and by the way, don't forget the way the notation works. F prime, F double prime, F triple prime. And you notice here, we just keep reapplying the same power rule. And this is what we end up with. Oh, okay. Wow. This is going to be fun. All right. Um, okay. So the first derivative, we already know how to do this. You're applying the power rule to each of these terms. Now here the k is 7, the n is 0, 1 rather, and here the k is the 10, negative 10, n is 0. So remember, we're applying the power rule here. Whoops. K, kx to the n. And so that's what we're doing down here in each of these cases. This last one, well, this one just goes to 0. I actually left it out. This one, I probably should have put a plus 0 there to make it crystal clear that that one goes to 0. This one just becomes 7. Okay. These, of course, you can see we've applied the rule, and we end up with 20x to the fourth plus 12x cubed minus 15x squared plus 7. So if you were only asked to do the first derivative, this is your final answer. But now we need the second derivative, so we're just going to apply the same rule to each of these terms. Okay. So let's do it. So here we have k is 20, n is 4, k is 12, n is 3, k is negative 15, n is 2. This is a constant, so it's just going to go to 0. So again, we applied the rules here across the board, and we end up with 80x cubed plus 36x squared minus 30x. This term just dropped out to 0. So if you were being asked just to do the second derivative, this is your answer. Okay, now let's try the third derivative. And just as you would expect, all we're doing is reapplying the power rule to each of these terms. All right, so here we have 30, 3, n is 3, k is 80. Here, n is 1. And so you can see when we apply the rule, we're going to wind up with 240x squared plus 72x minus 30. By the way, if you're using polynomials, eventually, if you keep going on x, the fourth derivative, the fifth derivative, the sixth, eventually you'll end up with 0. Okay. You can see that the number of terms is shrinking and the exponents are shrinking too. Okay. So if you keep applying this rule, here, for example, the fourth derivative is written with, these are written with Roman numerals. So here, you just need to get up to the sixth derivative to wind up with 0. I just applied the power rule, by the way. And you end up with 0 eventually. You always will, as long as this is a polynomial. Okay. So that covers the 7 rules. But only, now if you notice, we've only applied these to relatively simple functions. What we have to do is now find out if there are any other rules for other types of functions. In particular, like I was saying before, when you start looking at logarithmic functions, exponential functions, you'll see that the rules can be very different. Not the procedures, but the way the results are done. In other words, the product rule is always the product rule, but the result of applying it to a logarithmic function will be different than applying it to a polynomial. And speaking of all that, what we're going to do now is take a little bit of a detour and consider how we would take derivatives for trig functions. Now, trig functions, there's a lot of these. Okay. Probably should be able to find a book. I mean, sorry, a book, a table in our book which lists them all. Okay. So, I mean, let's see. Let me just quickly go find it. Oops. Because there, as you can imagine, it can get very intense. Well, we're going to start by looking at the basic ones. Let me just see if I can find that table. It's usually at the very beginning of the book or the very end. Here we go. Oh no. Well, you know what? It's possible the tables are actually mixed into the chapter itself. Let's see if there's one here. What I'm really looking for is the trig functions. By the way, in here we've got other examples of what we've been doing where really what they're trying to do is show you how to deal with more complex cases. Like here, for example, what they're showing you is that you could, if you wanted to, calculate this maybe a little quicker with factoring, but even if you don't, you'd still end up with the same answer. Sometimes, you know, there are strategies you can use. Here we go. I think I just found it. Yeah, this is getting a little ahead of ourselves. Maybe we'll save this for later. What I wanted to do right now is just simply show you the basic trig derivatives, starting with sines and cosines. Okay. And then we'll see how to derive the others. In principle, because remember when we introduced reintroduce trig functions, you'll recall that really all of the other trig functions besides sine and cosine are really just functions of sine and cosine. Though if you know how to deal with the sine and the cosine, you should be able to do all the rest of them. So we'll start by introducing these two cases. The derivative of the sine of x is the cosine of x. The derivative of the cosine of x is the negative sine of x. And also, I don't want you to get confused with this notation. What you could write this in equivalently as the following. What this is saying is that if f of x is sine of x, then f prime of x is the cosine of x. Here, if you're told that the function is cosine of x, f prime of x is the negative sine. Make that cleaner. By the way, this is an area where you probably should think about memorizing these just to speed things up for yourself. I mean, you should probably be able to look them up, of course, but certain things you should probably try to memorize. I would say that these are among those things you should probably memorize. The trig derivatives, I mean. So here we go. Now, what do we do with something like this? Up to this point, when we had a product of some kind, it was always the product of two polynomials, which meant that we could simplify it and solve it directly with the power rule. Here we can't do that. We must use the power rule. So this is our f of x, a g of x rather, and this is our h of x. So remember how that works. So that means we have to figure out the derivatives of g of x, which we can clearly do with the power rule. H of x is a trig derivative, something like that. We're not going to derive it. We're just going to remember how it works. Okay, so g of x would be the 5x cubed, and sine x is the hx. Okay, so these are the original functions. So here we're using, of course, our favorite rule, the power rule. So if k is 5 and n is 3, that leaves us with n, k, x to the n minus 1, which is equal to 15x squared. And this one we were told, by definition, the derivative of the sine of x is the cosine of x. So that means we have everything we need. We have g of x, g prime of x, h prime of x. Now it's just a question of substitution. And this is what we end up with. Okay. And you can see there's nothing we can really do to simplify this. Although, you know, if you really put your mind to it, you can often find ways. You could do something like this, for example. But I'm not sure what that gets you. It's the same thing. Now, when you're dealing with trig functions, though, by the way, sometimes this is a very good approach because you might find that whatever's in parentheses will reduce to something much simpler. Yes, but like here, that isn't the case. But yes, there's so many different trig identities that it's always possible that by rewriting it like this, that you can find one of them, and it might reduce to something nice and simple like 1 or 0. But normally, we can just leave it like this. Oh boy, what do we do here? The quotient rule. Okay, so this is g of x. This is h of x. So we need to know g prime of x and h prime of x. All right, let me copy this to the next slide. Okay, that's the rule. So g of x is the numerator, cosine x. H rather is the denominator, 4x squared. So we'll solve for the numerator with our definition that we were given. The derivative of cosine x is negative sine x down here. Here we're using the power rule, and we end up with 8x. And now we plug everything in to our scary formula. And you can see right here, that's our final result. Wow. But again, it's really just straight ahead substitution. It was just a question of knowing how to find g prime of x and h prime of x. And then, when you plug everything in, now you notice I did simplify it just a little bit by multiplying these two out. But that's about it. There's no other obvious ways of simplifying this. So we'll just leave it like this. Well, I mean, tactically, I could divide out an x from these terms, but let's just leave it like that for now. All right, let's look at some of the other derivatives. Now, keep in mind, these are obtained ultimately from these two, based on the way they were related to the sine or the cosine. So to complete, actually, I'm going to copy this here. To complete our set of trig derivatives, I'll just sneak these in here. So you can see, because if you really were determined to do this, what you could do is say, well, listen, the tangent is itself the sine of the cosine, if you recall from the way it's defined. So if you went ahead, you could actually apply the quotient rule to this ratio, and you would ultimately end up with the secant, remembering that the secant of x is the inverse of the cosine. And so because it's squared, that means so in other words, when you apply the quotient rule, you'll ultimately end up with 1 over cosine squared of x, and that is the same thing as secant squared of x. That's why this is why it is this number. So if you want to get some practice with the quotient rule, you can certainly go ahead and plug in these numbers. And oh, I didn't remember. I guess I went ahead. I felt like, why not show it to you? All right, well, here it is. I actually did not remember that I'd already done this. So let's see the proof. Okay, what the heck? Let's look at the proof. So if g is the numerator is sine x. Okay, here we go again. Now, by definition, g prime of x, therefore, is the cosine of x. And here, h prime of x, by definition, is negative sine x. All right, so we're going to plug these into the quotient rule. So both h of x and g prime of x are the sine of x. So that leaves us here. Now g of x is sine x, that goes here. And of course, h prime of x, as we saw, is negative sine x. Now, these can be simplified. These two mean the same thing as cosine squared of x. This is actually becoming positive sine squared of x. Now, way back, you might recall that I showed you one or two of the so-called Pythagorean identities. And one of them was that anytime you have the cosine squared plus the sine squared, it doesn't matter what x is, this adds up to 1. Oh, and because the cosine is the inverse of the secant, that's it. So it actually proved to be a lot less painful than I expected. But this is the key to the whole thing right here. So without that, you would not have this result. So this is one of the so-called Pythagorean identities. It is implied by Pythagorean's theorem, Pythagoras' theorem. Oops. Uh, there's others. I still remember we may have gone through a couple of the others. But this is what I mentioned earlier. There's a lot of trig identities that will help simplify things, but it takes a long time to recognize them all. There's so many of them. If you look, if there's one in the book, you'll see that it's like it could take up a whole page. There's so many of them, maybe even more than that. So there it is. Wow. And here's the rest. And again, you could, if you wanted to, feel free to go through and prove these with the quotient rule, because all of these are ultimately quotients. The cotangent, if you recall, is 1 over the tangent, which in turn is the same thing as the cosine over the sine. Okay. So you would apply that to your quotient rule and you'd get the correct result, remembering that the cosecant, oops, just quickly reminding yourself that the cosecant of x is 1 over the sine of x. Down here, the derivative of the secant is the secant times the tangent. And then finally, the derivative of the cosecant is negative this cosecant times the cotangent. So again, I'm guessing didn't particularly notice it, but there's probably a page in your book somewhere that has all of these listed together. If not, you should be able to find it on the internet. It might be good to have it all together in one place while you're working on these problems. All right. Ooh, look at this one. Oh my God. So we have two different rules going on here. The entire expression is taken from the rule of sums, but this one will be coming from the product rule. So we're combining, this is often the case when we have messy expressions, we're ultimately just combining multiple rules in the same case. Wow, let's take a look at this one. So here's f of x, here's f. Now f prime of x, we saw already. If you start out with the cosecant, according to this chart, the derivative is the negative cosecant times the cotangent. Now, that means that this first term, oh, by the way, don't forget, this is going to be g of x and this is h of x. So what we're going to end up with is so we've already got g prime of x. Although I wrote it here as f prime of x. It's still, that's our g prime of x. It's the x times tangent x that we have to be careful with. This is a product. So let's think of this one as g of x and h of x. So g of x is x. We know that its derivative is 1. H of x is tangent x. And we just got through seeing that its derivative is, oh God, I lost it. All right. There, oh, no. Here it is, secant squared of x. And we proved that one. So when we apply the product rule, as you can see here. Let me just copy these real fast. G, this is our x. H prime of x is the secant squared of x. H of x is tangent x. G of prime of x is 1. This is the final result. So now we saw this is derivative is this one. Negative cosecant x cotangent x. And then the derivative here is the sum of these two terms. X secant squared x plus tangent x. Now, again, here, I don't think it's realistic to find a way of simplifying this. I mean, it's possible, but we'll just leave it like this. All right. Wow. Ooh, so we combine a lot with that one. The trig derivatives, the rule of sums, the product rule, all of them came into play here. Now, this is going to prove to be one of the most important results of all of calculus, the so-called chain rule. And what's happening here is that you're applying these derivative rules to a composite function this time. Basically, there's two different ways of writing this rule. And what's interesting about it is this notation you'll see in the book, this was given to us by Leibniz, but you could also write it like this. If you have a composite function f of g of x, derivative of this entire expression is equal to the derivative of this inner function times the derivative. I'm sorry, this is the outer function. Sorry, this is what when we have a composite function, think of this as the outer function and the inner. So what you're seeing here is that when you differentiate this entire composite function, you're basically finding the derivative of the outer function times the derivative of the inner function. Okay, now this one is very complex, very involved. We're going to need a lot of practice with this one. So I don't want to rush through it. But let me just show you what this is all about. This is the kind of thing you're going to use it for. You've got this polynomial and the entire thing is raised to the fifth power. Now, you could actually raise that to the fifth power and then use the power rule to solve for each individual term, but it's going to be very messy and time consuming. The chain rule, as it's called, will let us do this much more quickly because this is a composite function. You can think of this as f of g of x, where g of x is 5x cubed minus 2x squared plus 3 and then the f of x is x to the fifth. So then we can apply the rules. Now, we're going to use this notation because this is what the book is doing, but also it has certain advantages. And so we're going to introduce this new variable u, and we're assuming that original function is a function of u, and that u represents the so-called inner function. Okay. So y is f of g of x, y is the outer function in effect, and u is the inner function. If you're writing this result in differential form, which remember looks like this, then what you're actually doing is breaking up into two parts. We find the derivative of the outer function with respect to u, and then the inner function with respect to x. So you're multiplying two derivatives when you use this notation. Okay, so we're going to use that to come up with our solutions. But because this is such a complicated idea, I think maybe we can save this till next time. You'll need to recover from all this other material anyway. But certainly what we could do too is we can grab some more examples and run through them, because this kind of material does require a lot of practice. So what we could do is finish up the chain rule and then maybe go through some new examples and work on them just to make sure everyone's on the same page before we go on to whatever's next. This, by the way, is the end of what I'm calling section 2A. By the way, I borrowed this from another book. What they've done here is they're showing you how the chain rule would work with trig functions. We'll get back to that in a bit. Oh, and yeah, one more thing we have to do here. We have to show how to take the derivatives of inverse functions. Okay, wow. And then in 2B, we're 2B. Oh, we've got more fun coming up. We're going to look at other, oh boy, we're going to also introduce our inverse trig functions, apply the chain rule, and then we're going to introduce the concept of implicit. Oh my God. Yes, we have a lot to do here. But I do like the idea of stopping for a bit and doing more examples before we get into more in-depth territory. So first we'll finish up this section 2A, and then we'll go into the book and we'll grab a bunch of new examples and we'll work through them. And then we'll move on to 2B. By the way, in chapter 3, we're going to be looking at applications of derivatives, which will maybe help make it more understandable what exactly we're doing here. But for now, we're basically learning all the rules. And so once you've got the rules down, it then becomes a question of recognizing when to use each one. That's when the challenge starts to come in, trying to make sure you know when to use each rule, not just how, but when to use it. All right, so I think, like I said, I think that will be enough for now. We'll stop here, and when we pick it up, we'll dive into the chain rule, and then we'll take it from there, okay? All right, so I'll see you all next time.